Hi, this is Dr. Bay, and here's Bugsy. And today we're going to talk about carbonyl reductions to alcohols. We'll delve into hydrides as a reducing agent, as well as organometallic reducing agents like Grignard and organolithium. So stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Recall that in an oxidation reaction, the oxidation state of carbon increases, whereas in a reduction reaction, the oxidation state of carbon decreases. To better visualize this, here is an oxidation ladder going from a primary alcohol at the bottom to a carboxylic acid at the top. But today, we're going to only focus on what types of reagents facilitate a reduction reaction to form primary alcohols as shown in this oxidation ladder, as well as the formation of secondary alcohols as seen in the next oxidation ladder. We can use a reducing reagent that acts as a type of nucleophile that can be used to reduce ketones or aldehydes into an alcohol. Shown here is a general reduction scheme where a nucleophile attacks the electrophilic carbon of a carbonyl. Simultaneously, the double bond of the carbonyl breaks to form a new lone pair on the oxygen atom. This forms a tetrahedral intermediate. Then O- attacks a proton source, such as a protic solvent, or through what's called a water workup to eventually form the alcohol product. There are two types of nucleophiles that can be used to reduce carbonyls to alcohols, and you can use either a hydride like H-, or you could use a carbon nucleophile through an organometallic reagent. So let's get into more details on what these are. There are two types of hydrides, and you want to make sure that you're using the correct type for each respective reaction that you're trying to undergo. The first type is one that you've seen before, sodium hydride. This reagent can be rewritten as Na+ and H-, where the H- acts as a base to deprotonate an acidic hydrogen to form an alkoxide ion. And you've seen this before in Williamson ether synthesis, but it is not used in a carbonyl reduction. The second type of hydride source includes two new reagents, sodium borohydride or NaBH4, as well as lithium aluminum hydride, which can also be written as LiAlH4, or sometimes it's even seen as LAH. In both cases, H- acts as a nucleophile that attacks the electrophilic center of a carbonyl, and you can see both of these structures down below. Now let's go over examples of how each of these reagents are used in carbonyl reduction reactions. Sodium borohydride, or NaBH4, is a mild reducing agent that is often used with a protic solvent like methanol, ethanol, or even water. In this reaction, we're going to convert a ketone with NaBH4 in methanol to a secondary alcohol. In this mechanism, the boron-hydrogen bond is our nucleophile and attacks the carbon of the carbonyl. The second arrow goes from the CO double bond and breaks to form a new lone pair on oxygen, which essentially forms our tetrahedral intermediate. Then O- gets protonated by methanol to form a secondary alcohol product. Lithium aluminum hydride, or LiAlH4, can also be used to reduce carbonyls to alcohols. The main difference between LiAlH4 and NaBH4 is that LiAlH4 is a much stronger reducing agent and actually reacts violently with water or any protic source. This means that protic solvents cannot be used with LiAlH4, and a protic source like water or H3O+ must be added as a separate second step. So in this reaction, we're going to convert a ketone with LiAlH4 in the first step, and then use water in the second step to form our secondary alcohol. The mechanism is actually quite similar to the last one, where the aluminum-hydrogen bond is our nucleophile and attacks the carbon of the carbonyl. Then the CO double bond breaks to form a lone pair on oxygen. Then O- gets protonated by water to form a secondary alcohol. Now let's go over how to form alcohols by using organometallic reagents. The first organometallic reagent is called organolithium, and it is a carbon nucleophile that 1. Reduces carbonyls, and 2. Makes a molecule larger by adding more carbons. In this reaction, we are reacting a ketone that currently has 5 carbons to form a tertiary alcohol that has 6 carbons. So notice we are increasing that carbon count by 1 carbon. The first part is to prepare your organolithium reagent by turning an electrophile into a nucleophile. So because we increased our carbon count by 1 carbon, we're going to start with an alkyl halide that only has 1 carbon. This will react with lithium metal in ether or Et2O to form methyl lithium. Because carbon is more electronegative than lithium, we actually can rewrite this ionically as CH3- and Li+. Then in the second part of this reaction is we're going to take our newly formed nucleophile CH3- and that will attack the carbon of the carbonyl. The CO double bond will break to form a tetrahedral intermediate, and then that O- will get protonated by water, which is again called a water workup, which then forms our alcohol product. So as you can see, the mechanism other than the formation of the organolithium reagent is quite similar to that of using either NaBH4 or LiAlH4. The only difference is rather than having a hydride as your nucleophile, in this case, you're now using a carbon nucleophile. Another type of organometallic reagent is called a Grignard reagent, and it acts very similarly to organolithium. The first part is to prepare your Grignard reagent by turning an electrophile into a nucleophile. Again, because we increased our carbon count by 1 carbon, we're going to start with an alkyl halide with 1 carbon. Then this will react with magnesium metal in ether, or Et2O, to form methyl magnesium bromide. And because carbon is more electronegative than magnesium, we can rewrite this as CH3- and MgBr+. And then the second part is we're going to take our newly formed nucleophile, CH3-, and that will attack the carbon of the carbonyl. The CO double bond will break to form a tetrahedral intermediate, and then O- will get protonated through a water workup to form our alcohol product. Some common mistakes when using organometallic reagents is first, you want to make sure that the water workup occurs after the reaction as a second step. Secondly, Grignard and organolithium reagents cannot be used on compounds with acidic hydrogens. So if your starting molecule has any alcohols, amines, carboxylic acids, or terminal alkynes, the acidic proton will actually get deprotonated instead, while the carbonyl stays untouched, which is not what you want to happen in these types of reactions. Another common mistake is that you cannot use an organometallic reagent for SN2. It's a different type of nucleophile that does not react with alkyl halides through an SN2 mechanism. And lastly, make sure that your carbon atoms never have more than 5 bonds, and that goes for any type of organic reaction, not just organometallic ones. Pentavalent carbons are a no-no. So in summary, you learned 4 new reactions to reduce carbonyls to alcohols. If you do not want your carbon count to change, then you can use a hydride source such as NaBH4 or LiAlH4 to form your alcohol product. But if you want your carbon count to increase, then you can use an organometallic reagent like organolithium or Grignard to form your alcohol product.